Homework 5, problem 11, find the polarization alpha for a hydrogen atom in its ground state. The charge density for the electron of a hydrogen atom in its ground state is given by this function, where this E and this E are different. This is the charge of an electron. This is the base of the natural logarithm. A little confusing, but you know, we run out of letters pretty quickly as we go further and further into physics, so it's a consequence we have to pay. Now, one of the things is this A naught is something called the Bohr radius, and you hear it often said that that's, you know, about how far away the electron is in a hydrogen atom. But if you were to plot this expression, you'd get this red curve, which definitely doesn't, I mean, it doesn't make A naught seem interesting at all. There's nothing fancy happening there. But what is interesting is then when you think of asking how does probability work, well, with probability you have to multiply the distance away with the surface area of a sphere at that distance. And so if you multiply r squared times your probability density, you get this blue curve, which does have a peak at A naught. And so I just wanted to plot that. That's an interesting thing, even though the red it does not look interesting, does not make A naught seem special. A naught is special. It's because of this expression, that r squared times rho peaks at A naught. And so it becomes the most probable location, the most probable distance away at which you find an electron in a hydrogen atom is the Bohr radius. Okay, so you didn't need to know any of that, but it was fun to talk about. In order to do this problem, we're going to do what we did before, right? We're going to say that the total force given any displacement is equal to 0, and so that means the force on an applied electric field has to be minus the force on the electric field from the charge cloud. The Q's are going to cancel out of this, so this is immediately going to imply that the applied electric field should be minus the electric field from the charge cloud. And now we need to find out what the electric field from the charge cloud is for some separation distance d, right? And so to do that, we're going to use the fact that we have a spherically symmetric distribution, and we're going to use Gauss's law. And so we draw a sphere at some radius r, and then we apply Gauss's law. So Gauss's law says that the integral of the flux through the surface d2x in hat dot electric field with an epsilon naught, I always forget, this is the electric field due to the charge cloud, of course, is equal to the volume integral d3x, volume through the surface, of our charge density, of our rho of r. In our case, this is actually pretty simple. We've got high symmetry here, and so this is simply going to be surface area 4 pi r squared epsilon naught times a radial component, right, of this electric field due to the charge cloud at a distance r, is going to be equal to, and then here we're going to have 4 pi, then an integral from 0 to r dr prime of r prime squared rho of r prime. And so here again you see this r squared rho of r prime type of stuff, and so that's why this A naught is interesting. Going and plugging stuff in, of course, this is going to give so ignoring the 4 pi, this is minus e over pi A naught cubed times the integral from 0 to r of dr prime of r prime squared exponential, now I'll write this as an exponential, minus 2 r prime over A naught. And so now I have to evaluate this integral. The way I like to evaluate these integrals is, of course, to use Mathematica, And so here is the integral evaluation from Mathematica. So just taking this and moving on, we're going to say that, right, we have the electric field due to the charge cloud at a distance r, right, or at a distance r, is going to be equal to, so all I'm going to do is divide by r squared and epsilon naught. And so minus E over epsilon naught d squared. Then this expression, notice I even stuck the a naught cubed into the integral here because it was more, the answer is more symmetric. 1 over 4, so the 1/4 will factor out actually, 1 minus, and then the a naught squared can go in, so this will be 1 plus 2 r over a naught, r over a naught, so this is a naught r divided by a naught squared is r over a naught, plus 2 r squared over a naught squared, times the exponential of minus 2r over a naught. Okay, so close the square parentheses and close the curly parentheses. There we go. Okay. And there's a pi I missed. And so that's what the electric field is. Now this has to be minus the applied electric field, and so the minus is simply going to cancel this out. And so this says that the applied electric field, right, and is going to be in the radial direction, is E over 4 pi epsilon naught. And then I'm going to get 1 over d squared, and I get this big huge thing, this 1 minus this stuff. Okay? But now I have to use the hint. The hint was to expand for r less than a. Well, in that I have this expression, the exponential of x. The Taylor expansion is very well known. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus dot dot dot. Okay, it's the very well known, very easy to do one there. And so this is going to be 1 minus 2r over a, not minus, plus 2r over a naught squared, and then 1 minus 2r over a naught, so that's this first term, it's just that, and then plus 1/2, and then 2r over a naught squared, plus 1/6 2r over a naught cubed, and I think that's far enough. Okay. And so now we just have to multiply everything out. And so this is just like a big FOIL here. 1 minus 1 times 1 is 1. Okay? And then 1 times minus, okay, this 1 times that one, that's minus 2r over a naught. This one times that one is plus 2r over a naught. So obviously those cancel. Right? And then next will be 1 times that one. And so this is a 1/2, 2 squared, so that's going to be plus 2 r squared over a naught squared, and then 1 times this one will be plus 2 r squared over a naught squared, and then this one times this one will be minus 4 r squared over a naught squared. So these plus 2 minus 4 again are going to cancel. And we keep going. And so here, okay, I'm putting I have a minus there that needs to be distributed, so I'm just keeping track of that with the parentheses. If that's all right for a moment. Now, moving on, we're going to have this 1 times this expression, which is 8 over 6. So this will be 8 over 6 r cubed over a naught cubed. This one, I'm going to have this 1 times that one, so that's a plus 2 times a plus 2, so that's a 4 plus 4 r cubed over a naught cubed. And then I'm going to have this one times this one, which is a minus 4 r cubed over a naught cubed. So those two go away, but that one doesn't cancel. Everything else, okay, is going to be higher. It's going to be r to the 4th over a naught to the 4th, and I don't need to worry about that. So looking at what I have here, this should be a minus, and that should be a minus, right? Because this is minus cubed, so minus cubed is still minus, so that should still be a minus. I have this minus here, that minus here, that's going to give me a positive. And I'm not sure where my D came from. This should have been an R, right? Should have been a little R. And so my applied electric field now is going to be E over 4 pi epsilon naught. I have a 1 over r squared, and then times an 8 over 6 r cubed over a naught cubed. Yeah, so obviously that, and this is going to give me 2/6 or 1/3. 2 or 1/3, and so yep. And so the applied electric field is now E over 3 pi epsilon naught a naught cubed times r, but I might recognize this E times r is just my the polarization, not the polarization, the dipole moment. And so solving for that dipole moment, right, I'm going to get the dipole moment is 3 pi epsilon naught a naught cubed times the applied electric field. And of course that says that this thing here, alpha, is 3 pi epsilon naught a naught cubed. Okay. So that was a tricky one, only because we had to do a Taylor expansion out to 3rd order. You almost never have to do a Taylor expansion out to 3rd order. This is a really cool case because the first 3 terms canceled, which is kind of fun. Okay.